When we were discussing conditions equivalent to having an isomorphism, you may have noticed that this last equivalent condition actually tells us something about the basis, about the dimension of V and the dimension of W. So let's suppose that we have an isomorphism from V to W, and let's suppose that the dimension of V is n. What can we say about the dimension of W? Well, we know that any basis of V gets sent to a basis of W. So if we take V1 through Vn, there has to be n vectors in a basis for V because V has dimension n. So V1 through Vn, a basis for V. But what we proved is that means that T of V1 through T of Vn is a basis for W. So the dimension of W, well, the dimension of W is just the number of vectors in a basis. And look, here's a basis. How many vectors are there? There's n of them, right? So the dimension of W actually has to be the same as the dimension of V. This maybe is geometrically, that seems plausible, right? If you have two subspaces that are isomorphic, our idea is that means they should look the same, and so in particular, they ought to have the same dimension. But this proves it, right? So that is, if we have an isomorphism, what we can say about the dimension. Well, if we know something about the dimension, what can we say about isomorphisms? So let's turn this question around. Let's suppose that we have a linear transformation from V to W, and suppose we know ahead of time that the dimensions of V and W are actually the same. Well, then it turns out that having an isomorphism is actually the same as being one-to-one and the same as being onto. This is not at all obvious because right, we know that having an isomorphism is the same as being one-to-one and onto simultaneously, but what we're saying here is you really only need to know one or the other. If these subspaces have the same dimension, you really only need to know one. You get the other one for free without any extra work. So the implication that 1 implies 2 and 1 implies 3, that's obvious. We've already proved those. So let's prove the reverse implication. So let's suppose T is 1-to-1. We'll prove that it's onto. So suppose T is 1-to-1. We want to show T is onto. Let's take a basis for V. So we know there are going to be n vectors in this basis. So basis for capital V. And then as usual, let's name the output of the linear transformation on all the V's. Let's name those W. Like this. Okay. Now, because T is 1-to-1, that means that our W's are linearly independent. That's a property of one-to-one linear transformations that we proved a while ago. Okay. So now we have n linearly independent vectors in W. The dimension of W is n, but the dimension of the span of W1 through Wn, because they're linearly independent, that's also n. So here we have an n-dimensional space sitting inside an n-dimensional space. That means that these have to be the same space, right? So span of W1 through Wn has to be equal to all of W. So now we have linearly independent W1 through Wn, and they span W. That means W1 through Wn. That means that all of W is a linear combination of outputs of this linear transformation, right? So if we take any linear transformation, any linear combination of these w's, like this, that gets hit by t by the same linear combination, but with the v's. So a1 v1 through an vn. Right? If we apply t to this and then use the linear transformation property to distribute the t hits all the v's, turns them all into w's, and we get this. So that shows that t is onto. All right. So now, supposing that these dimensions are both equal to n, let's show that onto implies one-to-one. So we need to assume that to show that something is one-to-one, you need to assume that t applied to v is equal to t applied to w. Okay, and then we're going to show that actually it's going to be a little confusing if I call these v and w because they're actually both in w. So let me call this one x1. Let me call this one x2. So these are both in w. Sorry, the x's are not in w. The x's are in v. x1 is in v, x2 is in v. T of x1, that's in w. And t of x2, that's also in w. So assuming that these are equal, what we want to do is show that x1 is equal to x2. Okay, well, as usual, let's let v1 and v2, we need to start with w's. So let's let w1 and wn be a basis for w. Okay, since t is onto, that means that there are v1 through vn, so that t of v1 equals w1, and so on down to t of vn is wn. Okay, but something that we showed about linear transformations is if you have linearly independent outputs, then your inputs had to be linearly independent. Well, our outputs are the w's, which form a basis, so they have to be linearly independent. So v1 through vn are linearly independent. So now we have n linearly independent vectors sitting inside of v. So they span an n-dimensional space inside of v, but v is n-dimensional. So that means that they have to be a basis, right? The span of these linearly independent vectors has to be all of v, and so v1 through vn are a basis for v. Well, since v1 through vn are a basis for v, that means that these two vectors way up here, x1, has to be a linear combination of the v's. So it's, say, a1 v1 plus dot 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 down to a n vn. And then the same thing for x2. x2 has to be b1 v1 plus dot 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 down to bn vn. All right. Now remember, we're assuming that t of x1 is equal to t of x2. And that means we can put these expressions for our x's inside of here. So we get t of a1 v1 plus dot 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 down to an bn equals t of b1 v1 down to bn vn. But then we can use the linear transformation property for v, so we get a1 t of v1 plus dot 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 down to an t of vn. And then the same thing on the right, but with b's. b1 t of v1 plus dot 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 bn t of vn. But so what is t of v1? Well, up here, right, t of v1 is w1. And same thing down to t of vn. So this is a1 w1 plus dot 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 plus a n wn. And on the right, b1 w1 plus dot 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 down to bn wn. Okay, well, why have all of our w's on different sides of the equation? Let's move them all to the same side of the equation. We have two terms with w1, so we can combine those two terms. We get a1 minus b1 times w1, and then, the same thing for all of the rest of them. We down to an minus bn times wn. And there's nothing left on the right-hand side, so it's just the 0 vector. Well, look, here we have a linear combination of the w's equal to 0. But the w's are linearly independent. That means that all of these coefficients have to be 0. So a1 minus b1 is equal to 0, and so on, all the way down to an minus bn has to be equal to 0. But that means a1 has to be equal to b1, and so on, down to an has to be equal to bn. That means the linear combinations that we started with, a1 v1 plus dot 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 down to an vn has to be equal to b1 v1 plus dot 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 plus bn vn, just because, right, these coefficients, I'm using different symbols, but those symbols, right, they're actually pairwise equal to each other. But this one on the left, that's x, x1, and this one on the right, that's x2. So remember, we assumed that t of x1 is equal to t of x2, and now we've shown that that implies that x1 is equal to x2, and that means that t is 1 to 1. All right, so this, yeah, it turns out that this was the hard one, but we did it. So if your dimensions are equal, then 1 to 1 and onto really mean the same thing. You only need one of them, and you get the other one for free, and both of them imply that you have an isomorphism. And this is a little surprising, because right, 1 to 1 and being 1 to 1 and being onto are actually sort of conceptually very separate. And for most combinations of dimensions, right, they mean very different things, but right, if you happen to have the same dimension, it turns out that they're the same.